All right, so we're back and we're still talking about Young's double slit experiment. Last lecture, last video, I introduced you to this concept of path length difference delta. And we looked at it in context of this central bright point. The distance between slit 1 and the central max we called R1. The distance between the second slit, slit 2, and the central max we called R2. Okay, and we saw that for the central maximum that those two values were the same. R1 and R2 were the same length, right? Because this line is in the middle, runs to the central maximum. Those two lengths were the same. I just had it up there, but I erased it. Now we're going to figure out R2 minus R1 for a different point on the screen. We're going to look at point P up here. Notice it's another point where there is bright light, like the central maximum. I could have chosen one of the dark places between the bright points, but I didn't. I chose the bright point number 3 up there. By the way, these bright points are known as bright fringes, okay, and the dark sections between them are known as dark fringes. They're known as fringes. Okay, so this is an example. This is the third. Actually, I'm not going to get into that. We're just going to say, I don't want to get into the indexing of those things yet. Let's just call this, say this is a bright fringe. Okay. The central max is also a bright fringe. All the bright spots are known as bright fringes. All the dark regions between them are known as dark fringes. Okay. Also, the distance between the slits I meant to make clear earlier, we're going to call D. Typically, just like in the video, in the Veritasium video, the D is a small number, some fraction of a millimeter. It certainly was when Young did the experiment, and is in our lab also. So D is a very small number, and that's the distance between the two slits. Let's now look at a different set of rays that leave slits 1 and 2. Remember, I made it clear before that when light passes through one of these, diffraction occurs, and on the other side, on the right side of the card of the slits, the rays point out in every direction. One of those rays is going to leave slit 1 and hit point P like that. Here is our new R1. R1 and R2 vary, they change as we move around the screen. Okay? They happen to be equal values for the central max. Here they're not going to be. So one of these many rays that leave slit 1 is going to eventually make its way to point P. That's the ray we've picked out here. And its length is R1. Okay? Similarly, some ray is going to leave slit 2 and also meet up at point P. See if I can do this without making a total disaster out of it. There we go. R2. These two waves are going to meet up and combine and interfere at point P in the same way that they met up and combined and interfered at the central maximum. Okay, a different set of rays. Okay, but there's interference at every point, including point P. R1 and R2 are going to meet up and interfere at point P. But in this case, R2 minus R1, that is, the path length difference, is not equal to 0. Because now R2 is bigger than R1. Okay. What does the path length difference equal? Okay, let's find out. We're going to find out, you'll be delighted, you'll be thrilled to know, we're going to find out what the path length difference is equal to in this case by using trigonometry. Woo! I know, I can feel it. I can feel it all the way from the future. You're excited about this. So we're going to draw a triangle here. Actually, we're going to draw a couple lines here. One of them is going to be a reference line that's going to run from the point between the two slits up to point P. Like that. So just draw that line if you're taking notes here. From the point between the two slits all the way up to point P, and we're going to call this angle here theta. There it is in all its radiance. Theta. Okay. Now, that's not the triangle. The triangle I think I'm going to do in blue. Might not be too bright, but it'll at least be different colored. I'm going to draw a line from slit 1 straight down to R2 such that they meet at a right angle like that. Okay, so that this is a right angle. It's not a right angle, it's a wrong angle. No, that's true. Okay, and we're going to complete the blue triangle right here. How's that showing up? Yeah, you can see that triangle. Make this a little thicker here. Okay. There we go. Okay, so that triangle there is the one that's interesting to us. Okay, I'll tell you why in just a minute. All right, but just draw that triangle. And it may not be obvious, but because D is much, much less than L. D is typically a fraction of a millimeter, L is meters, so we're talking about a difference of like 1,000 times here. L is approximately 1,000 times D, which means that down here close to the slits, these two rays are essentially parallel, R1 and R2. And if that's true, then this angle here, at the top of our triangle, is also theta. Take a little bit of visualization to see that. But because D is much, much less than L, R1 and R2, so long as we stay down here close to the slits, R1 and R2 appear to be approximately parallel. Sort of like if I pointed both my fingers to the sun, they would look parallel on my hands, right? They wouldn't look like that because the sun's so far away that they essentially look parallel. That's what's going on, okay? Now what I want to show you now is that this section here, this section there of the blue triangle, this part here is the path length difference. That is delta. R2 has to go that much further, okay, than R1 does. Okay. This is the path length difference. That is R2 minus R1. And if you look at the triangle, you'll see that delta is equal to D sine theta, right? Because sine is opposite over hypotenuse. Here's theta. Opposite is D. The opposite is path length difference, delta, right? This is the opposite. The hypotenuse is plain old D, not delta, D. Okay. So the opposite over the hypotenuse is delta over D, which means that delta is D sine theta. That is our path length difference. It's not zero because theta is not zero. Okay. In this case, our path length difference is D sine theta. Okay. It's that lower part of that right triangle right there. That's how much further the light from slit 2 has to travel than the light from slit 1 on its way to point P. The two pink parts you see left here have equal length. This is the path length difference. Okay, so pigeonhole that, and we'll talk next about how this funky pattern shows up.